All right, we're moving right along in chapter 2 here. What we are learning about today is a couple new rules for taking derivatives. So you can see here the title of these rules specifically are product and quotient, but I want to kind of fit that into the rest of the curriculum so you understand what that's about. So over here in the blue writing at the top of the page, right, these are the things that you have learned how to take derivatives of so far, right? If there's a power on x, you can take the derivative of that using the power rule. If it's sine, cosine, if it's e to the x and ln of x, right? I guess also you have taken derivatives of just plain constants, like if it's just a c, the derivative of 5, is 0. The world of math, right, involves lots of other types of functions that we need to be able to differentiate. So obviously what I've written here in the red is our attempts, right, to think about these other types of functions that we can encounter. So we've got the other trig functions, right, tangent, secant, cosecant, and cotangent. We've also got, not just e to the x. What if I have any number to the x power? So we'll learn about that in chapter 5. We've got the inverse trig functions here with inverse sine. And then kind of bigger groups here are functions that are products, quotients, composites, and functions that are made up of more than one variable. So those items, like these two, you're going to be learning in chapter 5. So it's going to be a long wait for those. And then all of these other items here, we're going to try to learn over the next couple days. So the product rule is the first one that we're going to look at. So as you can see, it's written here. Not all functions are written so that we can take the derivative using the power rule. Sometimes we have to use the other rules. So this rule is called product because you have one function f multiplied by a second function g. So if you look at example 1, here's f and here's g, right? We could FOIL this out and then take the derivative of each term individually, but we have the product rule, so we want to avoid that. Okay, so the product rule goes a little something like this. You have to identify what f and g are, and we take f, the first function, times the derivative of the second function, and we add to that the second function times the derivative of the first function. So f g prime plus g f prime, that's the product rule. All right, so now another little reminder here that you can say to yourselves is that this is the first times the derivative of the second plus the second times the derivative of the first. Important to remember, this is plus. Now, I learned this when I was in high school, and I repeat this to myself in my head every single time I take a derivative using the product rule. First times the derivative of the second plus the second times the derivative of the first. I'm doing that, right, quietly in my head. So here, okay, what's confusing, right, is now this function is called f, but we know it's comprised of these two first and second functions, right? So we're going to establish those derivatives. So f prime is going to be the first function, which is x squared plus 8x, times the derivative of the second, which is 12x squared minus 1, plus the second function, 4x cubed minus x, times the derivative of the first function, 2x plus 8. Now, for chapter 2, I don't need you to simplify this. I don't care even in the littlest bit if you want to multiply this out and combine like terms. I don't need you to do that. I need to measure at this point whether or not you know the product rule. So you can leave your answer in this format, okay, until I tell you otherwise. Once we get to chapter 3, you're going to have to simplify it. But for now, just roll with it, okay? Example 2, we've got x squared is going to be our first function, and sine x is going to be our second function. So when I write down the derivative of this, I'm going to write down the first times derivative of sine x is cosine x, plus the second function is sine x, times the derivative of the first, which is x squared, so that derivative is 2x. The end. Number 3 here, example 3, I have to identify 2x. I'm going to group that as the first term, and then I'm going to think about e to the x as the second function, and then I'm going to write down my derivative is the first times, now the derivative of e to the x is just literally e to the x, right? So I can do that, plus the second function times the derivative of 2x, which is just 2. Okay, so these unsimplified answers here are what I am interested in right now. Okay, every time you learn a new derivative rule, you're going to be asked to do a same old skill with it. So we were obsessed with finding equations of tangent lines in section 2.2. So now we're going to bring that, and do that for this new product rule that we have. So in order to find the equation of the tangent line, right, I know I'm going to be doing the same stuff as I did before. All I know so far is the x value of the tangent line, but I have to figure out what the slope is and then what the y value is. So I don't know, ordinarily I just always do the derivative first. So again, I'm going to group for x as f and cosine x as g, and then apply the rule. So first function times derivative of cosine is negative sine, plus the second function, which is cosine, times the derivative of 4x, which is just 4. Now, because I actually have to plug in pi, I might clean this up a little bit and write negative 4x sine x plus 4 cosine x. Kind of poor notation there because I guess I didn't really plug in pi yet, but let's do that here. Let's see, we've got negative 4 pi, sine of pi is 0, plus 4 times cosine of pi is going to be negative 1. So my overall slope here is negative 4. So I'm going to put that in that slope spot. And then to get the y value, remember, I'm going to plug pi into the regular function f. So 4 pi times cosine of pi, which is 4 pi times negative 1 again. So negative 4 pi is what is going to go into my equation. So this minus is going to become a plus, and I'll stick in there a little 4 pi. Ta-da! Okay, so that's all there is about the product rule. Okay, now we wouldn't have a product rule if there weren't a quotient rule. So, of course, this is how we take the derivative of rational functions, right? So if you look at example 5, that's a quotient, right? But, these are rational functions that we dealt a lot with when we looked at limits and stuff like that. So the quotient rule does have a little rhyme with it, and the quotient rule is a little bit more involved than the product rule. So when we write down the quotient rule, couple things. We're going to think of the bottom function as the low function, and we're going to think of the top function as the high function. And the little rhyme goes like this. It's low d high minus high d low all over the denominator squared we go. All right, now I'm not using perfect notation, and I didn't earlier when I wrote the product rule. I mean, if I was really, being so proper, I would make full function notations out of these. That's how you'll see it in the textbook. But I think just for our purposes, when we're trying to learn the rules, I think this format is better. So we sing to ourselves this little memory, this little song. It's low d high minus the high d low all over the denominator squared we go. Okay, and I'm going to perform for you one time only my famous yodeling. So to me, this sounds like it should be yodeled. So I always embarrass myself in class and do a nice little yodel with this quote-unquote song here. So I always picture it sounding like this in my head. Low-dee high minus high-dee low. All over the denominator squared we go. And that's how I sing it in my head. So enjoy it if you will, laugh if you must. But memorize it however you're going to do it. Okay, and then we'll just go through a couple little practices here. Same idea as before. Again, this is going to be the high function, right? So this is f and this is g. So when I establish f prime, I'm going to take the low, which just goes in parentheses, d high, which would be times 4x, minus the high function, 2x squared, times the derivative of the bottom, or d low, which is 2x, all over the denominator squared. And that's all you have to write for right now. I don't need you to distribute and simplify anything until, a problem calls for you to do that. This is good for now. Main thing to keep in mind is parentheses, right? If we have a sum or a difference, like here or here, we have to make sure that we have parentheses around our terms. Do another one here. Oh my, get out of my way. Do another one here with has a square root. So when we do example 6, we have to think of this like x to the 1/2 over sine of x. So this derivative is going to be low. D high is going to be a power rule minus high d low all over the denominator squared we go. So you can put that little squared in between the sign and the x. That means the entire quantity, right? That means this. Okay, those are the same exact notations. But again, you don't have to simplify or mess with anything else in example 6. Okay. Example 7 is here because I actually don't want you to use the quotient rule here. No quotient. What I want you to understand about the quotient rule is that it is built for a function of x, right? If we go back up here, a function of x divided by a g function of x, right? So when we have a constant, like here, number 6, our numerator is just the number 6, this is an alert that you do not have to use the quotient rule at all. You should be relying on the power rule for number 7. So you should rewrite this in your mind as 6x to the -3, and then take the derivative using a power rule. So that would be -18x to the -4, and that's how we would come up with our derivative for this one. We would avoid the quotient rule whenever we have a constant in the top or a constant in the bottom. Okay, because if you think about if it was like x cubed over 6, that's 1/6 x cubed. It's actually not rational at all, right? It's just 1/6 in front, and it's not a specific numerator denominator that are functions of x. Okay, so no quotient rule there either. So example 8 is what takes us on this little tour to learn about the derivative of the other trig functions. So if you're not aware, sine over cosine, right, that is the tangent function. So when we use the quotient rule here, we're actually going to establish what the derivative of tangent is. And it's going to have its own little rule that we're going to memorize going forward. So the derivative here is low, d high, minus high, d low, all over the denominator squared we go. Now this simplifies, of course, to cosine squared x plus sine squared x all over cosine squared x. And we know by our work with identities last year, right, that this is 1 over cosine squared x, and that is just really the secant function, right? So what we've come up with is a rule for the derivative of tangent, much like we have a rule for the derivative of cosine, okay? And all of these rules are existing here in this box. The other 4 trig functions, right, are here and here. So we want to start to memorize these and work with them more frequently so it doesn't seem like something you have to go out of your way to do. We just want you to work with it enough so that it becomes second nature. So it's like you've memorized it without having to do note cards or whatever. So for today, I mean, the best way to memorize it is to just rewrite these, write them down 10 times. I know that sounds crazy, but if you just repeat these down on paper, I'll float you a little extra credit if you want to email me, writing down this exact thing. The derivative of tangent is secant squared x. The derivative of secant is secant x tangent x. Writing those things down repetitively kind of commits it to memory. The other thing to notice here is that anytime there is a right, in front of it, like for cosine, cotangent, cosecant, each of those derivatives are the ones that have the negatives or the sign changes with them. So remember, the derivative of sine is cosine, but when we take the derivative of cosine, it's actually negative sine because of the sign change. So all the other cos are the exact same way. Example 9, I'll have you try on your own. And then I just want to try a little bit of work here with a numerical setup for taking these derivatives. So our work mainly today is about the product and the quotient rule. Okay, so I want to look down here at this example 1, and I want to do number 1 with you and see then if you guys can do some others. So part 1 here says given h1 of x equal to f times g, okay, see this product, our job is to figure out what h prime of 4 equals. That's what we're doing. So if I'm going to do part 1 here, I have to take the derivative of the h function, right, which is f times g. So literally, the derivative of h prime is the product rule. First times the derivative of the second plus the second times the derivative of the first. I can't really do anything more than write that rule down because f and g are not defined for me. So I can just kind of explicitly write down what their derivatives would look like if I knew what the functions were. Now I'm going to go ahead and plug in 4. So I'm going to take f of 4 times g prime of 4 plus g of 4 times f prime of 4, and that's going to give me my answer for number 1. So these are going to come from the table. So I am zeroed in right here on this row because this is the input of 4, gives me these 4 different outputs. So f of 4 from the table is 3. G prime of 4 from the table is 1. G of 4 from the table is 4. And f prime of 4 from the table is negative 1. So I carry that work out and I get 3 minus 4 essentially, right? So overall my answer up here is negative 1. Okay, part 2 is going to involve a quotient rule, right? Because they've defined this h2 function as a quotient. So it's low d high minus high d low all over the denominator squared. Okay, we're again plugging in 3 this time. So in order to calculate this, I need g of 3 as my first part of my numerator times f prime of 3, which is 0, right? I use this, then this, minus sign. F of 3 is 4. G prime of 3 is 1. And then going back to g of 3, that is 3 squared for my denominator, and I end up with 0 minus 4. For my top is negative 4, and my bottom is 9. So my answer for this guy here is negative 4/9. Okay. All right, so you can try example 9 and example 2 on your own now.